Now, good morning everyone. Continuing with the previous lecture, now today we will discuss some of the problems which are associated with the this peak time, settling time, rise time, and the percentage overshoot. Now let us consider a problem. We have to find, in this case we have to find the peak time, percentage overshoot, this settling time and the rise time for a second order transfer function which is given by this. So for solving this, first of all we want to know about the values of the damping ratio and the natural frequency of oscillation. So comparing this equation with this equation, that is P, that is omega n divided by s square plus 2 xi omega n plus omega n square. So comparing with this equation, we get the value of omega n equals to 10 and xi, that is damping ratio, is equals to 0.75. so we get these two values. Okay, now to find the value of TP, that is the peak time, we use this relation what we have derived earlier. So we use this equation of the peak time, and after calculating this, the peak time is equals to, the value of the peak time is equal to 0.475. Now we have to find the value of the percentage overshoot, as we have derived earlier. Percentage overshoot is given by this equation. Substituting the value of xi in this, the value of the percentage overshoot is 2.838. now again we have to calculate the settling time Ts, and the expression for the settling time is given by this. Ts is equals to 4 divided by xi omega n. So from this we get the settling time as 0.533. so this is the settling time. Now the only thing that is left is the rise time. As we already know that there is no analytical relationship for the rise time, so what we have to do, we have to use the table which is the table of the normalized rise time. That is, we have to use this table. In this case we have the normalized rise time, that is rise time into natural frequency, okay, which is versus the damping ratio. And using this table we see that for this damping ratio of, since the damping ratio in this case is 0.75, so for the damping ratio of 0.75 we get the value near about, for the damping ratio of 0.75 we get the value of rise time, we get the value of this normalized rise time, that is omega n rise time, as what's the value in this case is 2.3 seconds. Its value is 2.3 seconds. Now to get the value of the rise time, we divide this 2.3 second by omega n. Okay, so finally we are getting rise time as 0.23. So the rise time is 0.23, which can be obtained analytically, which cannot be obtained analytically while obtained graphically. So it is 0.23. So for this one, analytical expression is there, this is analytical expression is there, for this analytical expression is there, and this no analytical expression is there, but we can obtain by using the value of graph of xi versus the normalized rise time value. Now this problem actually demonstrates that we can find the value of TP, percentage overshoot, TS and TR without the task of taking an inverse Laplace transform, plotting the output response and taking measurements from the plot. So it saves a lot of time. Instead of going to the very tedious procedure, that is to find the inverse Laplace, then we find the response of the function, and then we can plot that function, and then we can measure all these values, so that is TP, TS, etc. We can calculate directly what's the values. It saves a lots of time. To come to the next example. Now given this polar plot, find the value of xi, that is damping ratio, omega n, then TP or percentage overshoot, and TS. Now from the previous lecture we know that damping ratio is equals to cos of theta, which can be obtained by using cos of tan inverse. In this case tan is 7/3, tan inverse 7/3. So the value that we get is 0.394. 0.394. Also the omega n is actually the radial distance that we have discussed in the previous lecture, radial distance from origin to the pole, and it can be obtained by the Pythagoras theorem, this and this. So this omega n can be taken as square root of, that is, it can be obtained by the square root of 7 square plus 3 square. So its value is given by 7.616, that is 7.616. Now peak over time. Now peak time, the expression for the peak time is given by this TP equals to y divided by omega d, and omega d in this case is the imaginary part. So this imaginary part is 7, that is pi divided by 7, which is equals to 0.449 seconds. 0.449 seconds. Now next is the percent overshoot. So the percent overshoot can be obtained by putting the value of xi in that. So finally we get the value of percent overshoot as 26%. Next is the approximate settling time. Approximate settling time is given by 4 divided by sigma d. Sigma d is actually the real part of that. So we get as 4 divided by 3, which is equal to 1.333 seconds. So these two problems that we have solved, and see that how these problems can be solved easily without going further plotting and all that tedious task. So it is very important part, and you have to do it and memorize these formulas also, so that when you want to solve it you can easily solve it. In the next lecture we can discuss about the poles and the zeros, effect of the poles and zeros. Thank you very much.